Hi guys. Today we will learn about Ferranti effect. Actually, if you guys understand the previous lecture, it's really easy. Let's see. Mm. So Ferranti effects, I said, first of all, it happened in the long distance of, line, power line, long distance of power line. And then because of in the line there's a C, you know the capacitor is really big. That's why it make it like a penalty effect. So it happened generally like at the night, at the night we don't use too much about our load, right, compared to the daytime. We need it like a power demand is compared to the daytime. Nighttime is kind of less, right? And or it could be like no load, no load situation at the long distance of power line. So the answer is, here's VS and VR. You can see this is the sending voltage end line here, and then this is the receiving voltage line. So which means that this is here is our house or our factory. You know what I mean? So we will say, so parent effect is simply this receiving part and the part of voltage is higher than this sending voltage end part. You know what I mean? So we will learn how to make it this page and why it happened. So it's a really easy, guys. First of all, in the okay, we need to first of all drawing the equivalent circuit. So this is a long transmission line, but as I said, compared to the L, R is the R is really small. Just on the lines resistance is really small compared to L. So we say just this part is impedance is JX, right? And then there's here's IS is coming, right? So we could say VS equal. We will make first of all we need to draw the equivalent circuit. Then we need to make equation, voltage equation. So VS is equal VR plus voltage drop, right? IS and JIS XS, right? And now we ignore this part, so don't worry about it. Don't worry about it. So this is I wanna show you guys drawing first. I guess it's better. Give us a. I will make it another. Give us a. Okay, we need to draw first. What is that? Equivalent circuit, right? So here's right. And I said R is just so small, right? Compared to X. So here's we say JX, right? And then here's our load. And this is our, equivalent circuit, in power system, general. So here is IL, line I, right? So first of all, we draw this, and then here is a sending voltage VS, and here is a VR, receiving end part. So we make equation VS equal VR plus receiving voltage plus voltage drop here, right? So J I X this one. So now we could drawing. So this situation is in sorry. This situation is in daytime. You know what I mean? When you use kind of lots of load. So there's a reference point is we need, right? This is a reference point. VR is a reference point. And then general situation, our current is lagging, right? Theta I line, right? And then J is, I said, 90 degrees precede, right? So 90 degrees precede is here. So it's so here's a voltage drop, I, J, X. So if we edit VR plus IJX is here. This is our VS. This is our general situation. So what happened in the Ferranti impact? So which means I will say here, load part, I will indicate just L. Mostly our load is motor, right? So which means L. So in the nighttime, so which means in the line, there's a capacitors, you know, right? In the line, the capacitance is really big. But no, daytime. I mean, in the line itself, the capacitance itself really big. So in daytime, this load L is really lots of energy state demand. So we need to give them more and more reactive power or power. You know what I mean? So we use a C. But in nighttime, what happened is here, in the lines C, you know, capacitor is really big. So, and then our load is demand is reduced. So what happened is at nighttime, so same equation, but I will draw it. So VR here, and then I, then in the nighttime, first of all, we know that we don't use too much of here's that. We don't use too much of load, right? So what happened is this. Our this is daytime. This is like nighttime. So our current is gonna be like this because there's a capacity, lots of capacitance, you know, compared to the load. So C is like so, which means you know, now this VR part, receiving end of voltage part, there's too much of reactive power. So we need to, you know, spend it, you know what I mean, observe to the line, you know what I mean. So that's why we add the C and then set the equation, following equation. So JX 90 degree, right? Yeah, 90 degree. So 90 degrees here. And then if we edit, here is a VS. So VR is here and VS is here. What happened is VR is you know VR part is more you know higher number. No, what I mean is the magnitude, voltage magnitude is more higher than VS. We could see this length, right? So VR is VS. What happened at this time? It could damage it to the load part, and this situation is not good penalty effect. You know what I mean? So that's why we wanna try to avoid this situation. So at this time, what we do is we add also L inductors. You know what I mean? To observe the reactive power. So what happened is here. Look at that. So red line. So for example, here's I, right? We add the I not I, L, right? L is lagging, right? Lagging. So if we add now current is here, right? But if we add L, what happened? Add these two current is it gotta be no this current is not yeah, this color. You guys can see current is it to change it to kind of a lagging part. Previous it was leading, but now lagging because we added L, right? So what happened here? So if we 90 degrees, we added here 90 degrees almost here, right? 90. So if we add it here, this is IJIX, right? For this drop. And then we draw here. What happened? Since we add L, to observe the reactive power from this part, VR part. What happened? Since we add L, this voltage is, getting bigger, right? And then, so which means we make it general our situation. You know what I mean? So that's why, in the power control system, we control the reactive power using L or capacitor. You know what I mean? So if we add the L means, we uh, we observe, you know what I mean, from the reactive power from the load. And C is which means we supply the reactive power. You guys may now you could make an image. You know what I mean? What I'm saying. So Ferranti effect is that. Yeah. What I said is. Yeah, that's our today's lecture, guys.